Welcome to today's Explainer. As a planetary scientist, I literally spend my days analyzing raw data from the most hostile yet incredibly resource-rich terrain in our entire solar system. And today, I am so thrilled to take you inside our latest mission briefing on exactly how we map the lunar South Pole. We're going to look at the exact data pipelines and orbital imagery we use to hunt for ancient ice, all while making sure our billion-dollar landers actually touch down in one piece. Here is the game plan for today's Explainer. We'll start with our target, the lunar South Pole, then look at how we use radar to hunt for buried ice. After that, we map out surface hazards using optical data, build some crazy detailed sub-meter 3D maps, and finally, fuse it all together to pick the absolute perfect landing site.
All right, part 1, target the lunar South Pole.
Let's dive right into this extreme thermodynamic environment. We are targeting ridges, specifically places like the Shackleton to Gerlache Ridge you see light here. Now, why here? Well, these ridges offer high solar illumination, which is absolutely crucial for rover power, but they sit immediately adjacent to these dark, freezing craters where sunlight literally never reaches. You see, because the moon's axial tilt is a tiny 1.5 degrees, these deep craters act as thermodynamic cold traps. They dip below 120 Kelvin, making them the perfect frozen vaults for ancient water ice. Moving on to step 2, radar hunting for buried ice. Before we can even think about landing a rover to sample that ice, we need to know exactly where those resources are hiding beneath the lunar regolith. And that brings us to a massive scientific hurdle. Seriously, how do we spot ice in total darkness? If these doubly shadowed craters never see the sun, standard cameras are completely useless to us. And more importantly, how do we distinguish a subsurface ice sheet from just a field of rough, scattered rocks? Because to a simple radar, they can look identical. The mathematical solution actually lies in our advanced radar instruments, specifically the dual-frequency synthetic aperture radar aboard Chandrayan 2. Traditionally, scientists just looked for a circular polarization ratio, or CPR, above 1.0 to find ice. But here's the problem. Rough rocks trigger a high CPR too. So to fix this, we introduced a dual validation method. We demand a CPR above 1.0, sure, but we pair it with a degree of polarization, or DOP, below 0.13. Together, these two metrics definitively isolate true volumetric ice signatures from a false positive rocky terrain. To put that into perspective, look at the data from our recent crater surveys. Notice how Faustini F2 hits our exact mathematical sweet spot. It's got high CPR and a DOP well below 0.13. That gives us a really strong signature for subsurface ice. In stark contrast, look at Shoemaker S3 and Cabeus R2. They might have a high CPR in certain places, but their DOP is way up there, well above 0.35. That negative correlation confirms we're just looking at rough, dry rock. No ice there. Now, as a planetary scientist, I absolutely love it when the geology physically backs up our radar data. Craters like Faustini F2 display this really unique lobate rim morphology. Basically, they have this flow-like lobed appearance and a remarkably shallow depth-to-diameter ratio of less than 0.16. This is the physical smoking gun, guys. It proves a past impact didn't just hit dry dust. It hit a hard, shallow target layer, like a consolidated sheet of subsurface ice, forcing the crater to expand outward horizontally rather than digging deeply. Okay, section 3. Optical, mapping, surface hazards. So, we know where the ice is, but finding it? That is only half the battle. Now we have to shift our entire focus to keeping our lander from crashing on the way down. Over 5,000. That is a staggering number of individual boulders, ranging from half a meter to nearly 8 meters wide, that our team had to manually map in just one proposed landing zone for the upcoming Israel-JAXA LUPEX mission. Think about that workload for a second. Looking at this incredibly high-resolution optical pass from the Orbiter High-Resolution Camera, or OHRC, you can really see the harsh reality of the lunar surface. Every single one of those tiny green dots is a potential mission-ending boulder clustered dangerously close to our target craters. And get this, over 99% of these boulders are under 4 meters in size. That means standard, lower-resolution orbital maps would have completely missed them. We don't just map these rocks for fun, right? We literally build explicit, hazard-aware contingency plans directly into our landing algorithms. We have to prevent very specific failure modes. For example, a lander tipping over on a slope greater than 6 degrees, a rover's wheels slipping on grades over 10 degrees, or even thermal runaway caused by landing in dark, heat-absorbing regolith. By mapping these hazards way in advance, we mitigate these critical failure modes before the rover ever leaves Earth.
This data translates directly into our engineering maps. By transforming that raw imagery on the left into the strict red and green hazard map you see on the right, we can define absolute boundaries. We strictly flag any area as a red hazard zone if there are boulders higher than 32 centimeters or if the local slopes exceed 15 degrees. Simply put, if it's not bright green, we do not land there.
Which brings us to Section 4, Building Sub-Meter 3D Maps. Here's the catch, though. To spot those tiny 32-centimeter rocks and calculate those exact slopes, we had to invent a completely new way to generate three-dimensional models of the lunar surface. The old standard was using 1-meter resolution maps from the Lunar Reconnaissance Orbiter, but that was leaving us totally blind to hazards hiding in the sub-meter range. So, by tapping into Chandrayan-2's OHRC data, we established a brand new standard, 0.30-meter resolution digital elevation models, or DEMS. Upgrading to this resolution isn't just nice to have, it's an absolute necessity for survival, allowing us to resolve individual small boulders and dangerous terrain hollows. Since our orbital cameras don't naturally take stereo pairs, we had to get creative and develop an opportunistic workaround. We basically identify overlapping orbital strips, ingest them into open-source pipelines, and run dense stereo algorithms to mathematically weave them into a 3D point cloud. It is so cool. This gives us stunningly precise 0.30-meter elevation models, transforming totally flat imagery into highly accurate topographical grids. Finally, Section 5, Picking the Perfect Landing Site. This is where all the puzzle pieces snap together, the ultimate test. We feed our radar ice detections and our optical 3D hazard maps into optimization algorithms to rank candidate touchdown coordinates. Take a look at our primary site, SLS 54, and the alternate, ALS 01. Our algorithms ensure these exact ellipses offer safe slopes, clear Earth visibility for radio communication, continuous sunlight for at least 14 days, and most importantly, they are right next door to the ice we mapped earlier. Now, this fusion of data isn't just some academic exercise. It's the exact framework actively being utilized right now. Using radar for resources and optical data for safety is the ultimate roadmap. It's guiding the upcoming NASA Artemis missions and the ISRO-JAXA LUPEX missions safely to the surface. It is, without a doubt, the new gold standard for planetary exploration. When we present these findings to Mission Control, we stand proudly by this rigorous methodology. By combining advanced polarimetry with sub-meter 3D topography, we are incredibly confident that our dual validation completely eliminates the risk of a rover blindly chasing dry rocks. We want to ensure every single watt of power is used to hunt for actual water ice. So having seen the raw data and our mapping pipelines from a planetary scientist's perspective, I leave you to wonder, with the hazards mapped out and the ice finally pinpointed, what completely new, unexpected mysteries will we uncover when our next generation of rovers finally touch down in those frozen shadows? Thank you so much for joining this explainer, and as always, keep looking up.